All right, so last time we saw that we looked at ideal batteries where the battery had no internal resistance. So today, let's look at a battery that has internal resistance. So I'll just remind you of what we had with ideal batteries. So from last lecture, we had something like this where we would have a resistor connected across with a battery. The current will go this way, and this is R, so this is current I. So with this, using the loop rule, all right, so in this, using the loop rule, we had the following. So with loop rule, we had E minus IR equals 0. Therefore, the current through the circuit is given by EMF over the resistance. And we know that the EMF E, so we say that in an ideal situation, the EMF is just equal to the potential across the battery. So if we want to look at a real battery, so we can say that for a real battery, we can say that the battery is connected in series with a small internal resistance. So we have our battery again, and then we have a small internal resistance connected in series with it, and then we connect our regular resistance R. So this is E again. We shall use lowercase r for the internal resistance and uppercase R for our external stuff. So this is the battery right here. It has an internal resistance. So again, using the loop rule, again, this time we have E minus I R minus uppercase I R again equals 0. So this time EMF is equal to I, and then you have lowercase r plus uppercase R. Therefore, the current through the circuit is given by EMF over R plus little r, where we can say R plus little r is called the equivalent resistance of the circuit. So you are familiar with equivalent resistance because we talked about that 2 days ago. So I can be written as E over R equivalent. Okay, so that is what we have for a real battery. Okay, so now we can now get the potential drop across R, the resistor. So we'll say that the potential drop across the resistor R is equal to the current times the resistance, which can then be written as EMF over uppercase R plus little k R multiplied by R. And we can write this as so we can write the potential drop across R to be equal to E, and then you have R over R plus little r. And we can do the same for the battery also. The potential drop across the battery is equal to the current again, multiplied by R, little r, plus, we'll start off with E minus current times little r. Okay. So the potential drop across the battery can then be written as E minus I. I is equal to E over R plus R, like that, and multiply that by little r. So this gives us the potential drop across the battery. So potential drop across the battery can be written as, so after a little bit of calculation, it comes out to be E R over big R plus little r. Okay. So what this tells us is that if the internal resistance of the battery is 0, R is equal to 0, meaning the battery is ideal, then we can say that the potential drop across the battery is equal to the EMF. So this brings us up to what is called a short circuit. We can look at how the resistance affects the battery when there's a short circuit. So for our battery, I'll draw it again. We have a small internal resistance, and then we have a load, which is the resistor across the battery. When you have a resistance with uppercase R, you can call it a load. Okay, so we can say this is a load across the battery. So we already saw that the current through this circuit is given by the EMF over the equivalent resistance, which is R plus lowercase r. So we can say that in the event, we can say a short circuit occurs. A short circuit occurs, there is no load. So in that situation, when there is no load present, you have something that looks like that. You have your internal resistance, and then the wire just connects across the battery just has a wire that goes from one positive terminal to the negative terminal. So this will be a short circuit, so there is no load. Therefore, the current through this battery can be written as EMF over R plus little r, where this part is equal to 0. So that you're going to have the EMF over lower r or lowercase r. So this is called a short circuit. This means that the current that flows through the circuit is going to be very high. So we can say, for example, if E is equal to 1.5 volts and the internal resistance is 0.02 ohms, what is the current in the circuit when there is a short, when it shorts? So we just want to calculate I in the circuit when there's a short circuit, meaning there's no load present. So we can do that pretty quickly. What is the current going to be? 75 amps, that's correct. So we can take the current I, which is just E over R, so it's 1.5 volts divided by 0.02 ohms. So this is 75 amps. Okay, so that's a large current going through. So typically, if you have a battery and you just connect one terminal to the next with a wire, the wire gets very hot because of the large current going through. That's what is called Joule heating. It heats up pretty quickly because of the large current going through it. Okay. Any questions on that? Okay, let's go to 31.6 parallel resistors. So we did series resistors last time, so today we shall look at the parallel resistors. Resistors can be connected. So we have our battery again, and I'll connect the resistor this way. So that's one of them, and I'll take a second one and connect it in parallel to it. So this will be R1. Let's call this R2. This is the EMF of the battery, and then there's a current I going this way. So this is a junction right here. So the current splits up into two. Let's call this I2, and let's call this I1. Okay, the same current goes across the resistor. So the current splits up into two. So here we shall use the junction rule first. The junction rule says the sum of currents in is equal to the sum of currents out. So we can use that. We'll see that the current I is the current going to the junction, and I1 plus I2 is the current leaving the junction. Then we'll say that by, if we look at each individual, if we look at two loops there, we'll see that the battery is connected in parallel across both R1 and R2. So we can say that by Ohm's law, the potential drop, so the total potential drop across the circuit, across the battery, is equal to I times an equivalent resistance, like that. Okay. So the current I in the whole circuit is given by the potential drop across the battery divided by R equivalent. And so this will also apply for I1, which is going to be a potential drop across the battery, or across R1, divided by R1. And I2 is a potential drop across R2, divided by, but by the loop rule, so if we take a loop across each element, we will see that the potential drop across R1 is just equal to the potential drop across R2, which is just the same as the potential drop across the battery. Okay, so we can now say that if we just if we say that I equals I1 plus I2, and we replace these I's by the potential drop divided by the resistance, then we can say potential drop across the battery divided by R equivalent is equal to potential drop across the battery, which is just the same as, which is the same for R1, plus potential drop across the battery for R2. So we can see that we can cancel out the potential drop delta V to end up with 1 over R equivalent equals 1 over R1 plus 1 over R2. So what this leads to then, if you like, we can write it as R equivalent equals R1, R2 over R1 plus R2. This comes from Of course, taking the lower case like that, R1, R2, and then doing R2 plus R1. Okay, that will lead you to this result. So we can now generalize to n resistors. We can say that if we have n resistors, R1 over R equivalent will be equal to 1 over R1 plus 1 over R2 plus 1 over Rn. Okay, that will be the equivalent resistance when you have n resistors. And if you want to write it in the form that I've shown you, then you can say that R equivalent is 1 over R1 plus 1 over R2 plus 1 over Rn, and then you take an inverse of that, and that gives you the same form, R equivalent. Any questions there?
Followed by -1?
Raised to -1, that will make it R equivalent. So here, this has a fraction. The one in the box has the fraction 1 over R equivalent, and the one outside is not a fraction, so you need to take the inverse of the terms on the other side of the equal sign. Let's now do an example. So try your hands at those two exercises. Those should be pretty straightforward, so I expect that you'll be able to do them. Okay, let's look at the solutions. A, what is the answer for the equivalent resistance for the first circuit there? So R equivalent is equal to, let's say, R1, R2 over R1 plus R2. That's pretty straightforward for this one. So we have 20 times 40 over 20 plus 40. So R equivalent gives you what? So we have 800 divided by 60, so 13.3 should be correct. Okay, let's look at the second one there. So B, what is R equivalent? Any answers? 0.769 ohms. Okay, so we can say R equivalent. Is everybody getting this result? 0.769.
I got 28.57.
Oh, 2.857 and 28.57.
Three different answers.
Yeah, that's good. 3 different answers. All right, so we use 1 over R1 plus 1 over R2 plus 1 over R3, and then do the inverse of that after you get it. So you can say R equivalent is equal to, what are the numbers? 1 over what? Okay.
Oh, so you couldn't use the previous one because it's only for 2.
That's for 2 years.
Oh, okay. Well, then mine's wrong.
Okay. So this is 0.1 plus 0.05 plus 0.2 in the inverse of that. So this would be
it's 2.85 or 2.86.
what is 2.86?
This answer.
So 0.35 inverse. So what is inverse of 0.35 is 2.86 ohms. Okay. So I believe that will be correct. Now, one thing I wanted to point out to you is when you have resistors in series, the equivalent resistance is always larger than the largest resistance in the circuit. When you have resistors in parallel, the equivalent resistance is going to be smaller than the smallest resistance in the circuit. So if you have a small resistance of 5, then your equivalent resistance should be less than 5. So that's how I know that it's correct. If I see an answer which says 28.5, I know that's not correct because it's larger than the smallest resistance. Okay. It should be smaller than the smallest resistance in the circuit if they are in parallel. Okay. So I'll make a note there for you. We'll say the equivalent resistance of the parallel circuit should be smaller than the smallest resistor in the circuit. Questions on that? Let's go to voltmeters next. So when we look at parallel circuits, one application of that is the use of a voltmeter to measure potential drop. So we can apply what we learned in parallel circuits to measure potential drop with a voltmeter. So let's look at an arrangement where we want to measure potential drop. So here, let's say that we have, and I'll use what is here. So we have a small internal resistance again. So we have an EMF, we have R, the current flowing, and that's uppercase R. So this is your battery again. The battery we now say has a small internal resistance, so it's a real battery. So in order to measure the potential drop across this resistor, so let's say the resistor is 17 ohms, as it says in your text. Okay, so to measure the potential drop across this battery, we will use a voltmeter, so we shall connect in parallel. So if you think of connecting it in parallel, then what you would have is, again, you have your battery. So this is our battery again. This is I, and this is R. So we'll connect the voltmeter in parallel to it. And let's say the voltmeter has its own resistance, RB, R subscript B for voltmeter. Okay. So we can find the equivalent resistance of this circuit. So that is what we have, since we have two resistors connected in parallel, the resistance R and the voltmeter resistance R volt. So for the voltmeter to measure this current, this potential drop without making any changes, it has to basically block the current, because now you see there's a junction right here. So we have I going through, there's going to be a current going through here. Let's call it I1 and the current I2. Okay, so for this voltmeter to work correctly and to represent the actual potential drop, I2 has to be very small. So we shall say for voltmeter to accurately measure potential drop, then I2 must approach 0. So the current I2 going through that branch must be very small. This means that the R volts must approach infinity. So it has to have a very large potential difference, a very large resistance, so that it prevents the current I2 from going through it. And if all that is true, this will be for an ideal voltmeter. If all that is true, then we can say R equivalent is just equal to R. R equivalent is equal to R for the resistor. Okay, so from there we can easily now see that the potential drop across the resistor is just equal to the potential drop R. So we can say that the potential drop across the resistor is just equal to the current through the resistance times R, which is what the voltmeter measures. So I want us to now get into resistor circuits where we can now get combined parallel and series resistors.